So this is somehow similar but different, very different from Euler cycle. What is Euler cycle? It's a cycle that uses all the vertices, visits all vertices. But let me just erase this part. I'm going to tell you just one property of this. The crucial property of this is every edge. Crucial fact is that every edge is used exactly once. So it's a cycle that uses every edge exactly once. That's Euler cycle. And Hamiltonian cycle is a cycle that uses every vertex now. Every vertex is used exactly once. So for instance, if our graph looks like this, then Hamiltonian cycle is like this. This is a Hamiltonian cycle. Okay? Because it used every vertex exactly once, and it returned to this original starting point. Yeah, it's fine that we don't use some edge. It's fine, as long as you used every vertex exactly once. That's a Hamiltonian cycle. Also, the precise definition is the following: a Hamiltonian cycle of a graph G is a cycle that uses every, that is the only condition, exactly once. Of course, we don't count the first starting and ending point twice. So, yeah, that doesn't matter for this first starting and ending point. This is an example of that. So for Euler cycle, there is a very simple way to check whether a given graph has an Euler cycle or not. Do you think it's also easy to find a Hamiltonian cycle? At first, this may look simpler because, you know, Euler cycle, we have more edges, but here we have fewer edges. We only have n edges if there are n vertices, right? Because every vertex is used exactly once. That means it's a kind of like an n-gon. The Hamiltonian cycle is really a cycle that looks like this. So there are fewer edges in a Hamiltonian cycle, usually. So it may look simpler than Euler cycles, but the thing is, it's much more difficult than Euler cycle. So there is no simple algorithm to find a Hamiltonian cycle, unlike Euler cycles. So determining whether a given graph has a Hamiltonian cycle or not, for each given graph, it can be a difficult problem. So let's see an example, simple example. Suppose we have a graph that looks like this. The G is this. Then, is there a Hamiltonian cycle of G? And you can easily see that G has no Hamiltonian cycle. But how can we show this? We don't have any criterion for this. So we have to work on each graph individually. So, why? Suppose there is a Hamiltonian cycle. The proof. Suppose that G has a Hamiltonian cycle. What does that mean? It visits every vertex exactly once. That means we have to use this edge, right? Because we want to visit 5, we have to use this and this edge. It must use the edges 4, 5, and 5, 2, because it must visit 5. Otherwise, you cannot have a Hamiltonian cycle. But similarly, because 3 must be visited, we have to use 3 and 4 and 3 and 2. We have to use this and this because we have to enter and then leave. And similarly for 1, 4, I'm not considering the order. What does that mean? We have to use all the edges, but it's not a cycle. If you use all of this, no, it's not a cycle. So it's not. So HC contains all edges, impossible. It's a contradiction. Because every vertex we have to use 2 edges incident to it. But here this says that you use all 3. It's impossible. So no, the assumption was wrong. So no Hamiltonian cycle. Like this, you can somehow prove that there is no Hamiltonian cycle, but there is no general way to show it. You have to really work on individual graphs carefully. Any question? So if the given graph is complicated, then this problem, finding a Hamiltonian cycle, can be a challenging problem. So unlike Euler cycles, finding a Hamiltonian cycle is not an easy problem. And actually, finding a Hamiltonian cycle, the Hamiltonian cycle problem is a famous problem known as what people call NP problem, if you have heard of this. Finding a Hamiltonian cycle is a well-known NP problem. So what does that mean? So there are some problems are called P problems and some problems are called NP problems. And roughly speaking, I'm not going to give you the precise definition, but roughly you can understand this. P problem. What is a P problem? The P means polynomial time. P problem is a problem that can be solved in polynomial time. Polynomial time means, so of course, the problem depends on the size of the input. So for instance, you have a graph with n vertices. Of course, if n is big, it will take more time. If there are like 5 vertices, then it's simple. But if there are like 1 million vertices, then even for checking whether there is an Euler cycle or not it will take more time because you have to check at 1 million vertices. But if you can solve this like polynomial time in n, that means if the input size is n, then you can solve this like in like n squared times or n cubed, something like that, polynomial in n. So if you can solve this in polynomial time, we think that this is relatively easy problem because polynomial is not a big number. Like n squared, of course, n squared grows fast, but compared to exponential function like 2 to the n, in fact, n squared is not a very big number. So we say that this is a kind of, in some sense, easy problem. Finding an Euler cycle, or determining whether given a graph has an Euler cycle or not, is a P problem. It's a typical example of P problem, because the input size is n, there are n vertices. You can check n times. For each vertex, you check once, right? It's like n, the polynomial time, you can solve it. And a problem is called NP problem. Doesn't mean that it's non-polynomial time. It's different. It's non-deterministic polynomial time, precisely. But you can understand this as follows. It's a problem that can be not solved, but that can be checked. Okay. How can I say? Whose solution can be checked. Can be checked in polynomial time. So it's an if I give you, it's an easy problem for students, I say, because you can solve this polynomial time. And what is this? This doesn't mean that it's a difficult problem. It's an easy problem for grader, I would say, TA. It may be difficult, but grading is easy. So for instance, finding a Hamiltonian cycle. If the graph is complicated, it's difficult to find one, but once you give me a Hamiltonian cycle, I can easily check whether this is correct or not, right? All you need to do is to follow this your cycle and then see if it visits every vertex once. It's very easy once you have a solution. That's what NP problem means. And a very famous open problem in computer science is whether n equals NP, P is NP. No one was able to say that this is correct or not. Maybe they may seem different, but people didn't, we don't know yet whether they are the same or not. Of course, some NP, all we can say is P is a subset of NP, but we don't know if this is a proper subset. Because, you know, for Hamiltonian cycle problem, no one was able to find a polynomial time algorithm to find a Hamiltonian cycle. Doesn't mean that there is no such algorithm. Maybe some algorithm is hidden, still undiscovered, but maybe there is such a thing. If you find a polynomial time algorithm to create a Hamiltonian cycle, that will solve this problem. Because Hamiltonian cycle problem is what's called NP complete. But I'm not going to say more details about that. So if you, maybe you have heard of this problem, right? P equals NP. Sometimes some people claim that they solve these problems, but so far they were all wrong. So it's a very famous problem, but of course difficult. No one knows whether this is true or not. And Hamiltonian cycle problem is one of the famous NP problems. Many problems are turn out to be equivalent to Hamiltonian cycle. Okay. Now we're gonna move on to the next page. 8.4, our shortest. Probably this will be kind of important application of graph theory, because it's really a real-life problem. You know, if you drive a car, you will probably use navigation, and your navigation system, if you want to go from here to, say, Busan, then it tells you which is the shortest way to get there. And there are many, of course, many ways to drive from Suwon to Busan, but the navigation will tell you this is the shortest one. But how does it find such a path? And this is tells you the algorithm. But before doing that, let me define one more definition. So weighted graph. A weighted graph is nothing but we put some number on each edge, because edges are not all the same. Sometimes, you know, okay, let me just first write this and then explain with an example. A weighted graph is a graph G in which every edge has a number attached to it. It's called weight. Usually positive. So for instance, A, B, C, D, we have a graph like this. And so there are 4 edges. And we have numbers. Let me use red. 1, 2, 3, 2, things like that. So each edge, we attach a number to it. So this number, yeah, it's nothing but just giving some numbers to each edge. And when we have a path or cycle, the weight of a path or cycle is the sum of the edges. Is the sum of the weights of the edges in it. So for instance, if you have a path like this, then what is the weight of this path? You just add numbers of the edges in the path. So 1 plus 3 plus 2 is the weight of this path. So why do we need such a thing? Why do we need edge? Because, you know, think of this as cities. There are 4 cities like A, B, C, D. Maybe Suwon, Bucheon, Seoul, like Busan. And there is a path like this. That means maybe there is a direct road from A to B, but you know the distance can be different. Sometimes the edges are not treated all the same, because sometimes this road is much longer than the other road. So it's important to consider the weight there. Okay? So for instance, let's say the weight is like 30. And yeah, so suppose you want to go from city A to city C. This is the direct path, but it takes a longer time if this is the time that you need to go from here to here. So you need to use this and this. But if you don't have this kind of information, you would probably use this path. So if you want to really model the real life problem, then you need to weight something like that. So we are considering weighted graphs now for this shortest path problem. Any question? Okay, let's see then the problem. So we have, think of this as a city map in some country. We have the vertices represent cities like A, B, C, D, F, G. And we have weights like 1, 2, 2, 3, 4, 4, 2, 5, 3, 1, 6. Okay? So we can think of this as city map, and the edge weight there are several ways, but let's say these are the cost to move from one city to another. Maybe you are traveling in a foreign country, and then you are in this city and you want to go to a different city, and you take a bus or subway or train. But if you want to go from one city to another, you have to pay some transportation fee that are recorded like this. So what is the cheapest way to go from A to H? So if you want to save your money, you have to choose your path wisely. So the question, what is the minimum cost to move from A to H? There are several different ways of doing that. Maybe this is too simple so you can see the answer immediately, but let's pretend that this is difficult and see, because we want to have some general algorithm. In other words, find the weight, or did I say weight? Let's see. Weight also is called the length. Also called the length. Weight. If you have a weighted graph, the weight means length means the sum of the weights. So weight. Find the length of a shortest path, because we want to say shortest. The length of this edge is 2. So the length of this path is 2 plus 4 equals 6. From some A to Z. So we have a graph, and you are given 2 vertices. What is with a weighted graph? What is the shortest path from A to Z? That's our main question in this section. Unfortunately, there is a nice algorithm. There is a polynomial time algorithm for this problem. There is a simple way to do that. There are several algorithms. I'm gonna tell you one of them. All right? It's called Dijkstra's shortest path algorithm. Let me explain that. Dijkstra's. He's a computer scientist, and I heard that he recently passed away, if I remember correctly, but not quite sure. It's a famous computer scientist known for his algorithm, finding shortest path. So it's an algorithm, so we must have an input and output. What are those? Input. Connected. If it's not connected, sometimes it doesn't make sense because you cannot even go from one to another. So we will consider only connected graphs. Connected and weighted. G. And edge weight, let's say edge weight W. So if you have an edge u comma v, then W of u comma v means the weight attached to it. So here W u v is the weight of edge u v, because weighted graph means we have weight, something like that. And 2 vertices, because we want to go from one place to another. Say A and Z. We want to go from A to Z. What is the output? I will tell you the length of a shortest path from A to B. So the length of a shortest path. There can be many shortest paths, but they have all the same length, because that's what shortest mean. The length of a shortest path from A to Z. It will tell you the length of a shortest path from here to here. So if you want to go from this place to this place, you have to pay this amount of transportation fee, things like that. Okay, what is the algorithm? Description of the algorithm. I'm going to explain this step by step. So first, So we have a graph, weighted graph. We're gonna put weight. We're gonna label the vertices so that that's shortest. That is the length of shortest path from the starting point to that thing. So let me do this first. Label the vertices. Initially, we label the vertices with numbers like this. The starting point is 0, and the other vertices will be labeled like infinity. All V different from A. Initially, we set the labels of the vertices like this. Only the A has label 0, and the other labels are infinity. And we're going to say that some vertices are active and some vertices are inactive. Initially, set all vertices active. Using active vertices, we will do something. So this is the initial setup. And then we're going to find an active vertex V with smallest label. Now we have a label for each vertex. So we consider all active vertices, and then we find a active vertex which has the smallest label. Find one such vertex. And then we're going to do the following. For each active vertex, say X adjacent to V. There are some vertices connected to V by an edge, right? And we will consider only active ones. And replace the label. This is the label of X. Replace this by the minimum of this. This is the weight between the edge between V and X. Okay? This is kind of lengthy, but I'm going to explain this again using a diagram or this example. And then make V inactive. So we are done with this V, so it will no longer play any role. And 3, we're going to repeat this step 2 until Z becomes inactive. So as long as Z is active, this will be iterated. It's like a while statement. And once Z become inactive, then we have the label for Z, then we return the label of Z. This is a description of the algorithm. In the if you look at your textbook, it is written in terms of pseudocodes, but I just explained that in a more natural language to us. All right. Yeah, if you just read this description, it will be quite difficult to understand. But if you look at the next example, it'll be better. Any question before I move on? Okay. So I'm going to use the same example I showed you. A, B, that's the G, H. Let me use this blue for the weight, edge weight. 2, 3, 4, 4, 5. This is the same example I showed you. Alright. What is the initial setup? We label the vertices with zeros or infinity. We want to go from A to H. So the A has weight 0. I'm going to label weight vertices using red color. So the other have infinity. Infinity, 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 infinity. You should think of this label as the cost you need to spend by going from A to that vertex. So initially we say that, of course, we are already A, so you don't need any cost going from A to A. But initially we said that it costs like an infinite amount of money. But we will update these costs one step at a time. And we set active vertex first. They are all active. They are all active. All right? I'm going to mark inactive vertex later on. So what is the smallest active vertex? Smallest active. Here. They are all active. What is the smallest active vertex? I mean the smallest label of active. Which has the smallest label? A. 0 is smaller than infinity, right? So A. So now, what's the next step? So we are done. This is the first step is done. We set up correctly. We label them. And now we are in the second step. Smallest active vertex. That is now what? A. Okay? Now what are you going to do? Now we look at every active vertex adjacent to V, the smallest thing. What are they? They are all active. So B and D are the candidates, right? We are going to update these labels. How do you do that? Just to make you understand this better, I'm going to redraw this again. But now I'm going to just omit the vertex numbers, vertex names. So this is 0. Now we have to update this. With what? Update this label by the minimum of the original label and LV plus the weight. This means if V is here and X is here, this means the cost that is required to this initially A using this path, right? So if you want to go from A and then V and then X, we have to add the cost up to V and then cost to use this edge. That's what this means, right? You add this number plus the cost over here. So what is that here? Infinity. If you go from A to B, what is the cost for that? 0 plus 2. 2 is smaller than infinity, so we replace this by 2, like that. What about this? If you go from A to D, the cost is 0 plus 1. 1 is smaller than infinity, replace this by 1. And the other things are the same. Okay? Now what? What did I say? Make V inactive. We are done with this. So let's say this means inactive. Now it's done. Now we repeat this. So now these are the active vertices. Find the smallest active vertex. What is the smallest active vertex? This one, D, right? Here now D is the smallest D is the smallest vertex. Now look at all the active vertices adjacent to this. We don't count this. We don't consider this, which is inactive. So we can consider these two things, right? Now I'm going to draw this little big diagram, and then I'm going to work on this diagram only. Because by now you have some idea what's going on. So let me draw this 0, 2, infinity, infinity, 1, infinity, infinity. So this is now an active. We are considering this. This is the smallest active vertex. Look at all the active vertices connected to this by an edge. Now here, let me draw the edge weights together. Okay? So if you go from this vertex to this vertex, what is the cost for this? You initially go from 0 to 1 is 2 and 1, and then 3. 1 plus 3 is 4. Smaller than this, so we will replace this by 4. 4 like that, right? What about this? You can go from here to 1 and then this. So 1 plus 5 is 6, smaller than infinity. You replace this by 6, right? Now we are done with this. So this is now inactive. This is done. Now look at all the inactive vertices and find the smallest one. Which is the smallest inactive vertex? This one, right? Now focus on this and consider all vertices active vertices incident to this, adjacent to this. 1, 2, 3, right? Now here, the original label is 4, but if you go from here to this point and this point, it's 2 plus 2. It's 4, so it's the same, so you don't have to do anything. But what about this? It's 2 plus 4, 6 is smaller than this, so you replace this by 6, like this. What about this? From here, 2 plus 2 is 4, is like 4. You replace this like that. We are done. So you now make this inactive. Consider all active vertices and find the smallest label there. There are 2. So it's fine. You can take anything, any of this. Let's say maybe this first. Let's say this is a chosen smallest active vertex. Look at all the active vertices adjacent to this. We have 2. So what is this? So if you go from here to there, here, and then here, what is the cost for that? 4 plus 3, 7. 7 is not smaller than this. So you don't replace this by 7. Because we replace this by the small minimum of this number and this plus this. With 6, so we don't do anything. What about this? 4 plus 1 is smaller than infinity, so you replace this by 5, like that. Now make this inactive. Now what are the, so we have 4 active vertices. This has the smallest one. So even though we have already labeled this, we are not done yet because this is active. We have to continue until this becomes inactive, because it may be replaced by a smaller number. We don't know yet. This is smallest possible. So here, only this vertex is the only active vertex connected to this. But if you want to go from here to here, the cost will be 4 plus 4, 8, not smaller than 6. So you don't do anything. So this now is made inactive. We have 1, 2, 3, right? This is the smallest possible, smallest label. So you replace, you look at all the edges, vertices connected to this. This is the only thing. But if you want to go from here to here, the cost will be 5 plus 6, which is bigger than this. You don't replace this. So it's done. Now you make this inactive. Now it's done because the destination is inactive. The output will be what? The label of this 5. So the algorithm says the smallest the minimum cost required going from here to here is 5. That's what algorithm says. Actually, it's a theorem. There's a theorem that the Dijkstra's algorithm always finds the smallest weight possible. This is something that we need to show. It's not clear. It's not trivial, but it can be shown. The theorem is that Dijkstra's algorithm always finds the smallest length. So it works, and this is not that difficult. I mean, it's a polynomial time algorithm.